I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Improbable. We'll look at some examples from probability theory. This is the area of math in which I make the most mistakes. An explanation can sound correct to me until it's shown that it's incorrect. It can often be very difficult to untangle the flaw in the original argument. So here's a simple example. Suppose two people are flipping coins until either a sequence of 3 flips produces heads, heads, tails, HHT, in which case player A wins, or heads, tails, heads, HTH, player B wins. Is this a fair game? Here's one argument. Both sequences have the same probability. For a fair coin, it's 1/2 cubed. Since both sequences have 2 heads, the coin doesn't have to be fair. Therefore, there is no advantage to either player. To me, that sounds reasonable. Too bad it's wrong. There isn't an arithmetic error or algebra mistake to point out as the flaw. The not very satisfying explanation is that the problem needs to be thought of in a different way. The key aspect being neglected above is that there might be more than 3 coin tosses before the game ends. This makes the 3 toss probabilities, which are in fact equal, irrelevant. To get either winning sequence, a heads has to occur at the beginning, so let's start with an H. From here, for a fair coin, H and T are equally likely, so HH and HT each have 1/2 probability. From HH, we could go to HHH or HHT. HHT ends the game with player A winning. But with HHH, the game continues, and we go on either to 4 H's, game continues, or 3 H's and a T. Ending in HHT, player A wins. Eventually, a T will appear, and player A wins. So player A is guaranteed to win the 1/2 probability from HH. Now let's look at HT. It could equally proceed to HTH, player B wins, or HTT, each of those have 1/4 probability. Player B now has 1/4 probability of winning, player A has a 1/2. From HTT, we could go to HTTT or HTTH, but HTTH is the same as starting all over with an H. So from HTT, we wait for the next H and start over. We could continue splitting up the probabilities from here. Again, at this point, it's 1/4 for B and 1/2 for A, so there's a 1/4 left. Or we could just notice that so far A has twice the probability of B, and that ratio would have to continue through our infinite probability sequence. So A will end up with 2 chances for every 1 for B. Overall, it's got to be 2/3 for A, 1/3 for B. To be fair, I've never seen anyone playing this game, and I doubt that it will catch on with the masses. However, it does point out how tricky probability can be. Also see the episode Game Shows. And it relates to a more substantial example. Many studies have concluded that there is no evidence for hot hands or streakiness. The most compelling evidence has been the analysis of sequences of successes and failures. Much like our H's and T's above, the standard interpretation of the data did not approach the problem correctly, and data that it was interpreted as implying no hot hands actually, when analyzed correctly, showed evidence in favor of hot hands. See the episode Hot for details. Here's another surprising probability problem. Many of the classes I taught had 20 or so students in them. If you have 23 people in a room, what's the probability that at least 2 people have the same birthday? 23 out of 365 is a little over 6%. The answer is much higher than that. This one is popular enough that you may have seen the answer. With 23 people, assuming no twins, it is very close to 50-50 that there is a birthday match. That seems crazy given that there are 365 or 366 possible birthdays. To compute this answer, you again need to approach the problem in a slightly unusual way. The complement is a powerful idea in probability. If you have a 0.6 probability, 60% of winning a game, you also know that you have a 0.4 probability, 40% of losing. Probabilities add up to 1. So the complement of 0.6 is 1 minus 0.6 equals 0.4. For the birthday problem, the complement is far easier to compute. To see why, start with the first 2 people in the room. Ignoring February 29, there's a 1 out of 365 chance that person 2 has the same birthday as person 1. Now put in person 3. If the first 2 birthdays are different, then there's a 2 out of 365 chance of matching a birthday. Continuing, you could hope that the probabilities will simply add up. 1 over 365 plus 2 over 365 plus 3 over 65, and so on. If you stop at 22 over 365 for 23 people, the sum is a little over 0.69, which is surprisingly large, but not alarming. However, if you continue to 30 over 365 for 31 people, the sum is 1.27, and there's definitely not a 127% chance of 31 people having a matching birthday. Instead, let's look at the probability that the birthdays don't match. The second one doesn't match with probability 364 out of 365. The first three don't match with probability 364 over 365 times 363 over 365, and so on. The probability that none of the 23 people match is 364 over 365 times 363 over 365, and so on, stopping at 343 out of 365, which computes to about 0.4927. If there's a 49% of not having a match, then there's a 51% of having a match. So how can we see that the second calculation is correct when the first one is not? Notice in that description of the 2 over 365, there was an if attached. To get a correct calculation there, we would have to adjust for the possibility that the first two did match. By the time we reach person 23, there would be a lot of possibilities. So, one last point. The 51% calculation, surprisingly large, assumes that all birthdays are equally likely. They are not. Some months have higher birth rates than others, and some situations make it more likely to have certain birthdays. Sports travel teams, grade level, and so on. So, given that, the real answer is a little bit higher than 51%, especially if you allow for the possibility of twins. Probability can be a lot of fun and give some surprising answers.